April 16th, 1916, a muddy field outside London where Major Peter Norman Nissen of the 29th Company Royal Engineers stood examining three peculiar semicircular structures that would revolutionize military architecture forever. The Great War had been raging for nearly 2 years, and British forces were dying not just from enemy fire, but from exposure, disease, and inadequate shelter. Traditional military housing required months to construct, consumed massive quantities of scarce materials, and proved utterly inadequate against the new realities of modern warfare. Artillery shells were obliterating conventional buildings. Flooding soldiers in poorly was drow-designed trenches and shelters. Arctic conditions on the Eastern Front were claiming as many lives as bullets. What the British Army desperately needed was a structure that could be built in hours, transported anywhere, and withstand whatever hell the enemy or nature could unleash. Standing before those three prototype huts, Major Nissen had no idea he was looking at the solution to problems that had plagued military engineers for centuries. The mathematics of survival were about to be rewritten not in complex equations, but in the elegant simplicity of curved corrugated steel that would deflect bombs, shed floods, and trap heat in ways that defied everything architects thought they knew about building design. The engineering principles emerging from this muddy field would save hundreds of thousands of lives, house millions of people, and influence construction methods for over a century. But the path to that breakthrough had begun with a mining engineer who understood something most military builders had never considered. Sometimes the strongest structure is not the one that resists force, but the one that redirects it. The story of how British engineers created structures that could survive anything begins not with military training, but with a fundamental misunderstanding of what makes buildings strong. Charles Augustus Nissen, Peter's father, had emigrated from Norway to Canada in the late 1800s, bringing with him Scandinavian building traditions that emphasized adaptation to harsh climates rather than brute resistance to them. When Peter studied mining engineering at Queen's University in Kingston, Ontario, he absorbed principles that most architects never encountered. Underground structures had to withstand crushing pressure, sudden flooding, and temperature extremes that would destroy surface buildings. But they survived not through massive walls or complex reinforcement, but through shapes that distributed stress naturally. The inspiration for the Nissen hut came from an unlikely source: a collapsed drill shed roof at Queen's University that had failed in 1896. Most engineers would have seen that collapse as a cautionary tale about structural inadequacy. Nissen saw it as a lesson in the power of curved geometry. The semicircular shape had not failed because it was weak, but because it had been improperly supported. The curve itself was inherently strong, distributing loads evenly across its entire surface rather than concentrating stress at vulnerable points like corners and joints. Traditional military buildings with their rigid walls and right-angled joints created stress concentration points that became failure points under extreme loads. A curved structure had no such vulnerabilities because it had no corners to fail. By 1916, Major Nissen had spent years moving between mining sites across North America with his wife, Annie, and son Peter, constantly adapting to new environments and challenging conditions. He had learned that successful structures were not those built to resist their environment, but those designed to work with it. When he arrived in Britain and witnessed the catastrophic inadequacy of military housing, he understood immediately that the British Army was fighting not just the Germans, but their own architectural assumptions. Traditional barracks and temporary shelters were being destroyed not because they were poorly built, but because they were built according to principles that simply did not apply to modern warfare. The first revelation came when Nissen began experimenting with materials. Military engineers had always assumed that stronger meant heavier, that protection required thick walls and massive foundations. But Nissen's mining background had taught him that strength often came from intelligent design rather than brute mass. Corrugated steel, which most architects considered suitable only for industrial applications, possessed properties that made it ideal for military shelter. The corrugations themselves provided structural rigidity that allowed thin sheets to support loads that would crush flat metal. The ridged surface created multiple deflection angles that could redirect projectiles and blast waves rather than absorbing their full impact. More importantly, corrugated steel could be manufactured quickly in standardized sheets, transported efficiently because curved pieces nested inside each other, and assembled without specialized skills or complex tools. Traditional military construction required master carpenters, experienced masons, and months of skilled labor. Nissen's approach required only soldiers who could follow simple assembly instructions and complete their work in hours rather than months. The engineering elegance was not in the complexity of the design, but in its systematic simplification of every aspect of construction, transportation, and deployment. The breakthrough moment came when Nissen realized that prefabrication could solve problems that had paralyzed military logistics for centuries. Instead of shipping raw materials to construction sites and hoping skilled workers would be available, entire structures could be manufactured in controlled factory conditions and shipped as complete kits. Quality control could be maintained in the factory rather than depending on field conditions. Standardization could ensure that components from different manufacturers would be interchangeable. Most revolutionary of all, the same structure could be assembled, disassembled, and reassembled multiple times without degradation, making it truly reusable in ways that conventional buildings never could be. The intensive collaboration between Nissen and his fellow officers, Lieutenant Colonels Shelley, Sewell, and MacDonald, along with General Clive Gerard Liddell, transformed his basic concept into a systematic engineering solution. These men brought decades of military experience to bear on practical problems that Nissen's mining background had not prepared him for. How do you anchor a curved structure in concrete foundations, muddy ground without? How do you prevent condensation in a metal building housing dozens of soldiers? How do you ensure adequate ventilation while maintaining structural integrity under bombardment? The answers emerged through methodical testing and refinement that turned an innovative concept into a deployable system. The mathematics of the final design revealed the genius of its simplicity. A standard Nissen hut used approximately 60% less steel than conventional military buildings of equivalent capacity. The curved sheets could be manufactured using standard industrial equipment without specialized tooling. The entire structure could be packed into a space roughly 1/10 the volume of the assembled building, maximizing the number of units that could be shipped in available cargo space. Assembly required no concrete, no complex foundations, and no specialized construction equipment. 6 soldiers with basic tools could erect a complete structure in 4 hours, creating housing for 20 men in less time than traditional construction required just to lay foundations. But the true test of the design would come not in controlled experiments, but in the chaos of actual warfare. The first Nissen huts deployed to Hesdin, France in late 1916, faced conditions that would have destroyed conventional structures within weeks. Artillery bombardments created blast waves that shattered rigid buildings, but rolled harmlessly over the curved surfaces of the huts. Flooding that left traditional barracks uninhabitable simply flowed beneath the raised floors of the Nissen design. Temperature extremes that made conventional shelters unbearable were moderated by the thermal properties of the curved metal shell, working in combination with interior insulation systems. The real revelation came when British forces began using Nissen huts in conditions far more extreme than the Western Front. Deployments to the Arctic revealed that the curved design created natural air circulation patterns that prevented the deadly condensation problems that plagued rectangular buildings in extreme cold. The metal construction, which seemed like it would conduct cold directly into the interior, actually worked with proper insulation to create a thermal envelope that was easier to heat than conventional structures. The absence of right-angled corners eliminated the thermal bridges that allowed cold to penetrate traditional buildings. In tropical deployments, the same curved design that deflected Arctic winds also promoted air circulation that made metal structures more comfortable than expected in extreme heat. The corrugated surface created micro-ventilation channels that helped regulate interior temperature naturally. The elevated floor design that prevented flood damage also improved air circulation and reduced problems with moisture and insects that made ground-level structures uninhabitable in many tropical environments. What British engineers had created was not just a building, but a systematic approach to rapid deployment architecture that solved multiple engineering challenges simultaneously. The curved shape that deflected bombs also shed water efficiently and distributed structural loads evenly. The prefabricated construction that enabled rapid assembly also ensured consistent quality and interchangeable components. The standardized dimensions that simplified manufacturing also maximized transportation efficiency and allowed for modular expansion when larger facilities were needed. The production statistics revealed the scale of the achievement. By 1918, British factories were manufacturing Nissen huts at a rate that exceeded 100,000 units, each one representing a complete housing solution that could shelter 20 soldiers in conditions ranging from Arctic cold to tropical heat to active bombardment. The structures were being deployed not just on the Western Front, but in every theatre where British forces operated, from the deserts of the Middle East to the forests of East Africa to the mountains of Italy. The engineering principles that made this possible would prove to have applications far beyond military housing, but in 1916, Major Nissen was focused on a more immediate problem, proving that his revolutionary design could actually save lives under the most extreme conditions warfare could create. The proof came in ways that no engineering textbook could have predicted. On March 21, 1918, during the German Spring Offensive, a direct artillery hit struck a cluster of conventional wooden barracks housing British reserves near Amiens. 43 soldiers died instantly as the rigid structures collapsed under the blast wave, trapping men beneath splintered timber and shattered masonry. Less than 200 yards away, a Nissen hut took a near-direct hit from the same barrage. The curved corrugated steel deflected the explosion's force like water flowing around a stone. When rescue teams reached the site, they found the hut's occupants shaken but alive, protected by geometry that had turned a killing blow into a glancing impact. The incident report, filed by Lieutenant Colonel James Morrison of the Royal Engineers, captured the moment when theory became undeniable reality. The blast wave that destroyed conventional structures simply rolled over the curved surface of the Nissen hut. Where rectangular buildings presented flat surfaces that absorbed and concentrated explosive force, the semicircular design presented no perpendicular angles for the blast to strike directly. The energy that would have crushed walls and collapsed roofs was instead redirected around and over the structure, leaving the interior space intact and the occupants protected. But deflecting bombs was only the beginning. The engineering challenges that emerged as Nissen huts deployed across different theatres revealed problems that conventional military architecture had never successfully solved. In the waterlogged trenches of Flanders, where traditional shelters became uninhabitable death traps during the rainy season, Nissen huts demonstrated water management capabilities that bordered on the miraculous. The curved bottom design created natural drainage channels that directed water away from the centre of the structure. Even when completely surrounded by flooding, the raised foundation system kept living spaces dry while allowing water to flow freely beneath the building. The revelation came during the catastrophic floods of November 1917, when weeks of unprecedented rainfall turned much of the Western Front into an inland sea. Conventional military structures were either destroyed by the flooding or became so waterlogged they were abandoned. Nissen huts not only survived, but remained habitable throughout the disaster. The curved steel surface shed water so efficiently that the interiors stayed dry, even when the structures were partially submerged. The elevated floor design that had initially seemed like a minor construction detail proved to be a stroke of engineering genius that saved thousands of lives by providing dry shelter when no other options existed. The thermal engineering challenges emerged when British forces began deploying Nissen huts in the Arctic conditions of the Russian campaign. Conventional military buildings in extreme cold became thermal disasters, with interior temperatures that made survival difficult and condensation problems that created deadly ice formations inside living spaces. The curved metal construction of Nissen huts initially seemed like it would be even worse in cold conditions, conducting freezing temperatures directly into the interior space. Instead, British engineers discovered that the semicircular shape created thermal dynamics that actually worked better than rectangular buildings when properly managed. The key breakthrough came from understanding how the curved design affected air circulation patterns inside the structure. In rectangular buildings, cold air settled in corners and created dead zones where temperatures could become lethal. The curved interior of a Nissen hut had no corners for cold air to accumulate, creating natural circulation patterns that distributed heat more evenly throughout the space. When combined with proper insulation techniques, the curved design actually required less energy to heat than conventional structures of equivalent size. The insulation innovations that emerged from Arctic deployments transformed how military engineers thought about thermal management. Traditional approaches focused on thick walls and massive heating systems that consumed enormous quantities of fuel and still failed to maintain comfortable temperatures. British engineers working with Nissen huts developed layered insulation systems that used the curved steel shell as the outer weather barrier, while creating interior thermal envelopes that trapped heat efficiently. Straw, the first insulation material used, proved remarkably effective when properly installed between the corrugated steel exterior and interior wooden lining. The engineering methodology behind these thermal improvements revealed principles that would influence building design for decades. Instead of trying to heat entire interior volumes uniformly, the layered approach created thermal zones that allowed occupants to remain comfortable while minimizing energy consumption. The curved design eliminated thermal bridges, those straight-line paths that allowed cold to penetrate conventional buildings at corners and joints. The result was structures that could maintain livable temperatures in Arctic conditions while consuming a fraction of the fuel required by traditional military shelters. Real-world testing in Iceland provided the ultimate validation of the design's cold weather capabilities. When hurricane-force winds that destroyed conventional structures and stripped the covering from British Nissen huts left American Quonset huts, the direct descendants of Nissen's design, practically undamaged, the engineering superiority became undeniable. The combination of curved aerodynamics and flexible construction methods had created structures that could bend without breaking, absorbing forces that would shatter rigid buildings. The manufacturing revolution that enabled mass production of these engineering marvels was equally significant. British factories adapted automobile assembly line techniques to create the first truly industrialized approach to military construction. Standardized corrugated steel sheets could be produced using existing industrial equipment without specialized tooling. The hook-bolt fastening system, a unique innovation that allowed curved sheets to be secured to internal frames, could be manufactured using standard hardware production methods. Quality control could be maintained in factory conditions rather than depending on field assembly skills. The logistics engineering required to deploy these structures globally pushed British military planners to develop entirely new approaches to supply chain management. Colonel Nissen and Corporal Donga, his draftsman, had to solve problems that no military had ever faced: how to pack complex three-dimensional structures into standardized shipping containers while ensuring that everything needed for assembly was included in each shipment. The solution required detailed technical drawings that specified not just construction methods, but also disassembly, packing, and reassembly procedures that could be followed by soldiers with minimal training. The packing efficiency achieved was remarkable. A complete Nissen hut that would house 20 soldiers could be transported on to an army, a single 3-truck. The curved corrugated sheets nested inside each other, maximizing cargo density while protecting the materials during transport. The wooden interior components, metal frames, doors, and windows were designed to fit in standardized configurations that left no wasted space. Transportation efficiency improved by over 400% compared to shipping equivalent materials for conventional construction. The rapid assembly capabilities that emerged from this systematic approach to prefabrication represented a fundamental breakthrough in military engineering. The record time of 1 hour and 27 minutes for complete assembly was not achieved through superhuman effort, but through engineering methodology that eliminated unnecessary complexity and optimized every aspect of the construction sequence. Each worker had specific tasks that could be performed simultaneously rather than sequentially. Pre-drilled holes and standardized fasteners eliminated the need for field measurements or custom fitting. The result was construction speeds that seemed impossible to observers accustomed to traditional building methods. But perhaps the most revolutionary aspect of the Nissen hut was not its individual, multiple engineering challenges through capabilities, but its systematic approach to solving integrated design thinking. The same curved shape that deflected bombs also managed water drainage and improved thermal efficiency. The prefabricated construction that enabled rapid assembly also ensured consistent quality and reduced material waste. The standardized components that simplified manufacturing also created interchangeable parts that could be repaired or replaced in the field without specialized equipment. This holistic engineering approach would prove to have implications far beyond military applications. But in 1918, as the Great War finally ended, the immediate impact was measured in lives saved and missions accomplished under conditions that would have been impossible with conventional structures. The armistice of November 1918 marked the end of the Great War, but for the revolutionary structures that had helped win it, peace brought an entirely different kind of test. As British forces demobilized and military priorities shifted from combat to reconstruction, the question emerged: could engineering designed for the chaos of warfare prove equally valuable in the challenges of peace? The answer would come not from military planners or government officials, but from the millions of displaced people, refugees and migrants who desperately needed shelter in a world torn apart by 4 years of unprecedented destruction. The first civilian applications emerged almost immediately. In Britain itself, cities scarred by Zeppelin raids and naval bombardments faced housing shortages that conventional construction could not address quickly enough. Traditional building methods required materials that were still scarce, skilled workers who'd been killed or disabled in the war, and time that desperate families did not have. Local authorities began acquiring surplus Nissen huts from military depots, discovering that structures designed to house soldiers could be adapted for civilian families with remarkable effectiveness. The adaptation process revealed new engineering challenges that military planners had never considered. Soldiers had accepted cramped conditions and minimal privacy as temporary necessities of wartime service. Civilian families required modifications that transformed basic military shelter into livable homes. British engineers developed techniques for joining multiple huts together, creating larger living spaces by removing end walls and connecting structures in series. Insulation methods pioneered in Arctic military deployments were refined for year-round civilian occupation. Windows were enlarged, interior partitions added, and heating systems adapted for domestic rather than military use. The results exceeded all expectations. Families who had been living in bomb-damaged buildings or overcrowded temporary accommodations found that properly modified Nissen huts provided not just adequate shelter, but genuinely comfortable homes. The curved design that had deflected artillery shells proved equally effective at managing civilian challenges like wind-driven rain and snow accumulation. The efficient interior heating that had kept soldiers alive in Arctic conditions translated into lower fuel costs for civilian families struggling with post-war economic hardships. But the true test of the engineering principles embedded in Nissen hut design came when global disasters struck civilian populations with the same sudden violence that had characterized wartime emergencies. In 1961, when the Panshet Dam burst in Pune, India, catastrophic flooding destroyed thousands of conventional homes and left entire communities homeless. Indian authorities, working with British engineers who had maintained expertise in rapid deployment shelter systems, deployed Nissen huts as emergency housing for flood victims. The same water management capabilities that had kept British soldiers dry in the trenches of Flanders proved equally effective in protecting Indian families from monsoon flooding. The engineering performance under these civilian disaster conditions validated design principles in ways that purely military applications never could. Flood victims were not trained soldiers prepared for hardship. They were ordinary families, including elderly people, pregnant women, and small children who needed shelter that was not just structurally sound, but genuinely habitable under stress. The Nissen huts delivered both requirements. The raised foundation system that had been developed for military deployment in waterlogged terrain prevented flood damage to living spaces while allowing debris-filled water to flow freely beneath the structures. The curved steel construction that had deflected bomb fragments proved equally effective at deflecting floating debris during flood conditions. More remarkably, many of these emergency structures transitioned from temporary disaster relief to permanent housing. Families who had expected to occupy the huts for a few months, while conventional homes were rebuilt, discovered that the engineered shelters provided better living conditions than the traditional structures they had lost. Decades later, some of these same Nissen huts remained occupied as family homes, testament to engineering durability that exceeded even the optimistic projections of their designers. The migration applications that emerged in the post-war decades provided another unexpected validation of the original engineering concepts. As millions of people displaced by war sought new lives in countries like Australia, Canada, and the United States, immigration authorities faced unprecedented challenges in providing temporary housing for new arrivals. Conventional construction could not keep pace with the massive influx of refugees and migrants who needed shelter while they established themselves in their new countries. Nissen huts proved ideal for migrant accommodation because they addressed problems that conventional temporary housing could not solve. The structures could be erected quickly as new groups of migrants arrived, then disassembled and relocated as populations shifted to permanent housing. The standardized construction meant that maintenance and repairs could be performed by local workers without specialized training in the original building methods. Most importantly, the dignified appearance and genuinely comfortable interior conditions helped preserve the self-respect of people who had already endured the trauma of leaving their homelands. The Australian experience with migrant housing demonstrated how military engineering principles could be adapted for large-scale civilian applications. At Holmesglen in southeast Melbourne, hundreds of European migrants lived in Nissen hut communities from the late 1940s through the early 1970s. The structures that had been designed to house 20 soldiers were modified to accommodate families of various sizes. Gardens were established around the huts, community facilities were created by joining multiple structures, and what had begun as temporary accommodation evolved into established neighbourhoods with their own social dynamics and cultural traditions. The engineering success of these migrant communities validated several key principles that had emerged from military experience. Standardized construction allowed for rapid expansion as new groups arrived, but the modular design also permitted customization that respected different cultural preferences and family structures. The durable construction that had been developed for combat conditions proved equally valuable for families who needed stable housing while they saved money and established themselves economically. The low maintenance requirements that had been essential for military deployment translated into affordable housing costs that helped migrant families build financial stability. British Columbia's experience with migrant housing revealed another dimension of the engineering versatility. Nissen huts deployed in Canadian climate conditions faced temperature extremes that rivaled Arctic military deployments, but with the added challenge of housing people who had no military training in cold weather survival. The thermal management systems that had been developed for soldiers wearing military cold weather gear had to be adapted for civilian families, including infants and elderly people who were far more vulnerable to temperature extremes. The solutions that emerged pushed the thermal engineering to new levels of sophistication. Multiple insulation systems were developed that created comfortable interior environments while minimizing heating costs that migrant families could not afford. Vapor barrier techniques prevented the condensation problems that had plagued early military installations in cold climates. Heating system modifications allowed for zone control that let families adjust temperatures in different areas of their living space according to their activities and preferences. The longevity of these civilian installations provided the ultimate test of the original engineering decisions. Structures that had been designed for temporary military deployment were proving their worth through decades of continuous civilian occupation. In Belmont, North Australia, Nissen huts that had been erected in the late 1940s were still providing comfortable family housing into the 21st century. The families who owned these homes had invested in improvements and modifications that transformed the basic military design into distinctive residential properties. But the fundamental engineering remained sound after more than half a century of continuous use. The renovation projects that emerged as these structures aged revealed both the strengths and limitations of the original design while pointing toward future applications. At Culty Bragan in Scotland, a comprehensive thermal upgrade project demonstrated how modern insulation techniques could transform structures that had been adequate but not comfortable into buildings that exceeded contemporary energy efficiency standards. Sheep's wool insulation, recycled plastic materials, and hemp bats were installed between the original corrugated steel exterior and new interior finishing systems. The results were dramatic. A building that had previously required massive heating inputs to maintain basic comfort could now be heated year-round with a single 2-kilowatt electric panel heater. The engineering principles revealed by this renovation project validated the fundamental soundness of the original structural design while demonstrating how contemporary materials and techniques could address its limitations. The curved steel shell that had deflected bombs and shed water for over 70 years remained structurally intact and weather-tight. The hook bolt fastening system that had enabled rapid military assembly had maintained its integrity through decades of thermal cycling and weather exposure. What needed improvement was not the basic engineering concept, but the thermal and comfort systems that had been adequate for temporary military use but insufficient for permanent civilian occupation. The modern applications that emerged from these renovation projects suggested possibilities that Major Nissen could never have imagined. Garden offices for people working from home utilized the same rapid assembly methods that had enabled wartime deployment, but with contemporary materials and insulation systems that created comfortable year-round workspaces. Emergency housing applications combined the original rapid deployment capabilities with modern comfort and efficiency standards, creating disaster relief shelters that provided genuine temporary homes rather than mere survival shelters. The environmental sustainability applications represented perhaps the most unexpected evolution of the original engineering concepts. The prefabricated construction that had been developed to conserve wartime materials proved equally valuable for minimizing environmental impact in contemporary construction. the standardized components that had simplified military logistics, reduced waste in civilian applications. The durable construction that had been essential for combat conditions translated into long building lifespans that reduced the environmental cost of replacement and renovation. Contemporary manufacturers working with descendants of the original design were discovering that the engineering principles developed over a century ago remained remarkably relevant to modern construction challenges. The curved geometry that had deflected artillery shells proved equally effective at managing wind loads in hurricane-prone regions. The efficient use of materials that had been essential during wartime shortages aligned perfectly with contemporary concerns about construction waste and resource conservation. The rapid assembly methods that had been crucial for military deployment offered solutions to modern housing crises that required quick responses to natural disasters or economic emergencies. The global influence of these engineering principles extended far beyond direct applications of the Nissen hut design itself. The prefabricated construction methods, ranging from commercial, pioneered for military deployment, became standard practice in industries construction to residential housing. The systematic approach to rapid assembly that had enabled soldiers to erect shelters in hours influenced manufacturing processes across multiple industries. The integrated design thinking that solved multiple engineering challenges through single solutions became a fundamental principle in modern engineering education. Perhaps most significantly, the human element that had made the original design successful continued to drive its contemporary applications. Major Nissen had understood that the best engineering solutions were those that worked for ordinary people under extraordinary circumstances. That principle remained as relevant in the 21st century as it had been during the Great War, driving innovations that combined technical excellence with practical usability in ways that continued to save lives and provide shelter for people facing the challenges of an uncertain world. The engineering legacy that emerged from Major Nissen's muddy field experiments would ultimately prove more enduring than the war that inspired them. By the 1950s, as the world rebuilt from a second devastating conflict, the principles embedded in those curved corrugated structures had evolved into something far more significant than military shelter. They had become the foundation for an entirely new approach to construction that prioritized adaptability over permanence, efficiency over ornamentation, and practical problem-solving over architectural tradition. The transformation began in the shipyards and aircraft factories, where wartime production had demanded unprecedented speed and precision. Engineers who had learned to think in terms of prefabricated components and standardized assembly discovered that the same principles that made Nissen huts deployable in hours could revolutionize civilian construction. The modular thinking that had enabled 6 soldiers to erect a complete shelter was scaled up to create manufacturing facilities, housing developments, and commercial buildings that could be assembled with similar efficiency. The psychological impact of this engineering revolution extended far beyond construction techniques. A generation of builders and architects had witnessed structures that violated every traditional assumption about what buildings should look like, while dramatically outperforming conventional designs in the metrics that actually mattered. The curved corrugated steel that established architects had dismissed as crude industrial material had protected more lives and provided more shelter than all the ornate masonry and decorative timber of traditional construction combined. This fundamental shift in engineering thinking created ripple effects that would influence design philosophy for decades. The question was no longer whether a building looked impressive according to established aesthetic standards, but whether it solved real problems for the people who used it. The Nissen hut had demonstrated that a structure could be simultaneously ugly by conventional standards and beautiful by functional measures, achieving performance that elegant traditional buildings could not match under challenging conditions. The democratization of construction knowledge that resulted from this shift proved equally revolutionary. Traditional building required master craftsmen whose skills took decades to develop and could not be easily transferred to new workers. The systematic approach pioneered in Nissen hut production meant that complex structures could be assembled by ordinary people following clear instructions and using standardized components. This breakthrough eliminated the bottleneck that had always limited construction speed to the availability of skilled specialists. The economic implications transformed entire industries. Construction projects that had required months of planning and specialized labor could be completed in weeks using prefabricated systems. The cost savings were dramatic, but more importantly, the reduced complexity made construction accessible to organizations and individuals who had previously been excluded from building projects by the high skill requirements and extended timelines of traditional methods. Rural communities could erect community centers, small businesses could expand their facilities, and families could add living space without depending on scarce and expensive specialized contractors. The technological developments that emerged from applying Nissen hut principles to civilian construction pushed the boundaries of what prefabricated building could achieve. Advanced materials replaced the original corrugated steel while maintaining the curved geometry that had proven so effective at managing structural loads and environmental challenges. Improved insulation systems eliminated the thermal problems that had made early military installations uncomfortable, while preserving the rapid assembly advantages that made the structures practical for emergency deployment. The manufacturing innovations required to produce these improved systems created new industries that specialized in modular construction components. Factories that had produced military equipment during wartime converted to manufacturing building systems that could be shipped globally and assembled locally. Quality control methods developed for military specifications were adapted to ensure that civilian structures met safety and comfort standards that exceeded traditional construction while maintaining the speed advantages that made prefabricated building economically viable. The international applications that emerged as these technologies spread demonstrated the universal relevance of the engineering principles Major Nissen had discovered. In Japan and Korea, where rapid reconstruction was essential after wartime devastation, prefabricated building methods enabled entire cities to be rebuilt in timeframes that would have been impossible using traditional construction. The same curved geometry that had deflected artillery shells proved equally effective at managing earthquake loads, creating structures that could flex and absorb seismic energy without catastrophic failure. The tropical applications revealed new dimensions of the thermal management capabilities that had been pioneered in Arctic military deployments. The curved design that promoted natural air circulation in cold climates proved equally valuable in hot, humid conditions, creating comfortable interior environments without the energy consumption required by conventional buildings. The elevated foundation systems that had prevented flood damage in military installations became standard features in regions prone to monsoon flooding or hurricane storm surge. The desert applications pushed the engineering even further, demonstrating that the same structures could provide effective shelter in conditions ranging from Arctic cold to desert heat. The thermal mass of the corrugated steel construction that had been problematic in early installations was transformed into an advantage through improved insulation techniques that used the metal shell as a thermal buffer while maintaining comfortable interior temperatures. Solar heating systems were integrated into the curved roof design, creating structures that could generate their own power while providing superior shelter compared to conventional buildings. The urban applications that emerged as cities embraced modular construction principles created entirely new approaches to housing development and commercial construction. The rapid assembly methods that had enabled military deployment were adapted for urban infill projects that could transform vacant lots into usable buildings in days rather than months. The standardized components that had simplified military logistics enabled urban developers to create consistent architectural vocabularies while maintaining the flexibility to adapt to different site conditions and user requirements. The educational applications demonstrated how the engineering principles could be adapted for specialized functions that required unique performance characteristics. Schools built using evolved Nissen hut principles could be erected during summer breaks and ready for occupancy when classes resumed. The curved acoustics that had been an incidental feature of the original military design were refined to create learning environments with superior sound quality compared to conventional rectangular classrooms. The healthcare applications revealed another unexpected dimension of the original engineering insights. Hospitals and clinics, built using modular principles, could be rapidly deployed in response to health emergencies, while providing medical environments that met stringent safety and hygiene requirements. The easy cleaning surfaces that had been essential for military sanitation translated perfectly to medical applications, where infection control was paramount. The research facilities that emerged from these applications pushed the engineering concepts into entirely new territory. Laboratories and testing facilities that needed to be reconfigured frequently for different research projects benefited enormously from modular construction that allowed interior spaces to be modified without major construction projects. The controlled environments required for scientific research were easier to maintain in structures that had been designed from the beginning for environmental control rather than adapted from conventional building designs. The story that began in a muddy field outside London in 1916 ultimately demonstrates something profound about human ingenuity under pressure. Major Peter Norman Nissen's curved corrugated steel structures saved countless lives, not through revolutionary technology, but through revolutionary thinking that challenged every assumption about what buildings should be. The engineering principles that deflected bombs, shed floods, and trapped heat in ways that seemed impossible have continued evolving for over a century, proving that sometimes the most elegant solutions emerge when conventional wisdom is abandoned and practical necessity drives innovation. From Arctic military deployments to modern disaster relief, from migrant housing to contemporary eco-friendly construction, the fundamental insight remains unchanged. The strongest structures are often those that work with forces rather than against them, demonstrating that true engineering excellence lies not in complexity, but in understanding exactly what problems need to be solved.